Hello everyone, my name is Matthew Rasmussen and I'm going to talk about quantum computing. So, what is quantum computing? Before we really jump into quantum computing, let's look at what we use on a daily basis or digital computers. So, all of these computers that we use are based on the von Neumann architecture. Von Neumann architecture is basically the way that your computer operates. It has the CPU, memory, storage, and an input-out device. And basically all computers, going from the largest of servers to the computer on your phone, operate with this architecture. So one of the main problems with the von Neumann architecture is the fact that there's something called the von Neumann bottleneck. That is that there's no way that you can get enough information from the RAM to the CPU. So the CPU is basically idling and not really doing anything. So let's get into three of the major quantum computing ideas, or really the three major quantum mechanics that really allow quantum computing to happen. The first one is the idea of superposition. Imagine if you spin a coin, and as the coin is spinning, what is it? Is it heads or is it tails? Well, the fact of the matter is that it's something in between, but it's not one or the other. It could be a mixture of the two. Another thing is entanglement. Now, entanglement is basically the premise that if you have one coin spinning and then I spin another coin, these two coins can be connected in some way so that if you stop one coin on heads, then the other one is always heads. Vice versa, if you stop the one with tails, the other one is tails too. And then the last thing is something called interference. Now, interference is nothing new to quantum computing itself. We had interference issues with digital computers. However, we've gotten to a point where our digital computers are built so well that this subject isn't really talked about. But essentially, interference is if you know that there should be a 1 coming from the output, but really the quantum computer says it's maybe 95% 1, but then 5% 0, then it's going to correct that issue to make it a 1. So it's really just like error correction and making sure that it all works together. Okay, so let's actually get down into the meat and potatoes of quantum computing. Quantum computing is really, instead of the classical bits, which are represented as a 0 or 1, and that is because of the electrical current going through it. If it's high electrical current, then it's 1. It's low, then it's 0. Instead, quantum computing kind of looks at it differently. It stores information in these things called qubits. And essentially, you have infinite number of different possibilities that you could put in that qubit. So essentially, one can equal 99,000, while the other one can equal 0. And there could be a value for each of those instead of a 0 or 1. This will dramatically change the way that we do computing, because it'll be able to allow us to store so much more information and also get information to the processor of that quantum computer. Now, the only issue is how big of a range do you want to allow that qubit to have? Because the only problem that with the range is that you have to figure out a way to precisely say, okay, if this is the vector of the qubit, it needs to be that for every single time you want it to be that vector. Now, this is much where the interference from the previous slide came in, is that these qubits are not always correct. I mean, today there's like a 60% fail rate on most quantum computers. So we need to figure out a way that we can make sure that we get this correct. But even if you just increase the range to 4, that drastically increases the number of possibilities you can have 64-bit instead of binary. It would be, if you could do 16, it would be hexadecimal. Or if you could do 10, it would just be decimal. And that would completely change the way that we are able to do problems and store information in computers. So let's look into kind of the future of quantum computing. One of the major things that quantum computing will be able to do extremely well is to basically make all standards of encryption useless. Essentially, the standard RSA 2048 encryption system that most of us use on a regular basis. In fact, that's the super secure version of it. A perfect quantum computer can break it in 10 seconds. Now, if you look at a classical computer, for example, the estimated time that it would take for it to break that encryption scheme is 300 trillion years. So that is crazy to think that this quantum computing can break it in 10 seconds. If a government is able to come up with this quantum computer organization before there's a new form of encryption that comes out of it, then they will be able to break into any encryption that you have on your computer or anyone in the world. Privacy will no longer exist for that short period of time until a new encryption scheme will be able to use quantum computing itself to further encrypt the data. And that would be really cool because it would make encryption completely bulletproof. It would not be able to be broken like the encryption is today, except it just takes a really long time. With quantum computing, it can be completely encrypted, and that would be something that is really cool. Another great use for quantum computing would be molecular modeling. Now, molecular interaction is something that is extremely complex, and today's computers are only able to analyze the most simplest of molecules. Since chemical reactions are essentially quantum in nature, a fully developed quantum computer should have no difficulty whatsoever analyzing the most complex chemical reactions. Now, if we're able to understand chemical reactions easily just by looking at a computer, because it will do the work for us, then we'll be able to develop things that will A, not only last longer, B, have a better understanding of any chemical or any molecule that's in our solar system. And with that, who knows what the possibilities could be. We could figure out why do cells mutate? What goes behind that? Can we figure out if someone's going to be capable of getting a disease because of that? Instead of the DNA, they can use these chemicals, reactions, to discover those things. That's just one small aspect of it, but you can also look at material science and figure out why something decays over time, or why explosions react in some way, or even there's a better form of nuclear power. I mean, the ideas are endless, and really it's just people who need to come together and use these things to figure it out. I mean, one of the main things would be pharmaceutical drugs and how fast that they could be studied. So just things that are crazy, the possibilities that could be come from quantum computing. The last aspect is really particle physics. And this is very much like molecular modeling. However, with particle physics, using particle colliders are extremely expensive, and there's not really many of them out there. And still doing actual experiments on particle colliders are is extremely important. But using quantum computers, you'll be able to simulate those particle colliders and what actually happens in them. And the two particles colliding against each other, you'll be able to simulate that in a program. And of course, you need to verify it by actually doing the experiment on the particle colliders. But we'll be able to let us understand so many more things because the quantum computer will be able to handle all those complex, time-consuming problems and steps to the equation extremely fast. And these are just some of the things that quantum computing can do that really will change the world for us. Any of the things that we think we don't know the answer because it's going to take too long to actually compute it, will no longer be an issue. Now, this does require quantum computing to be perfect, but considering how far we came with just digital computers, I cannot wait to see the next 50 years of the future of quantum computing. Because at this point, we are at the 50s or 60s with digital computers than we are with quantum computers. We're developing programming languages. And even IBM, you can go on their website and simulate a quantum computer. In fact, you can even book time on quantum computers. This is the future, and I'm excited to see it.